All right.
Whenever you're ready.
Yeah, let's start now, I guess.
All right.
All right. Cool. So anyways, all right. I'm Bubba. I've been running AI at home for like a few months now. I've been yapping about it. Steven has heard me in here every Friday since then, just yelling about it. And so then Steven said, hey, you should make this a talk. So we decided to do that. And damn, there's a lot of people here in this room. And I was not expecting that. A lot of new faces too, which is really cool to see. So this is just going to be like an introduction into AI and the little bit of like the software that's involved and like how to run it. And then and also talking about some reasons that you should run it at home and run things locally. And then, yeah, and I'm just going to yap about that and some of the things that you need to know. So anyways, why do you want to run AI at home? Well, first of all, it's going to keep all your stuff private, right? So if you're using AI and you're prompting it for like medical things, if you're trying to give it like financial information, those types of things, obviously you're sending that outside your house. You're giving that to tech companies who have that stuff. So keeping things private is always good. Always encrypt all the things, of course. But also, maybe some other concerns that you might have worries about, right? Like, these things could be, these are just theories, but they could be like thinking about how you are prompting the LLM, right? They could be thinking about like your thought patterns and that kind of stuff. I've heard of some people, this is just rumors on the internet from Reddit. Who knows what the validity is, but like people going into job interviews and the hiring manager saying, would you please show me your ChatGPT prompts so that I can read them and see how you think, right? Like stuff like that, kind of dystopian. So what are some of the benefits, right? So obviously my favorite thing is the fact that I get to own my tools. I don't like having subscription models. I don't like having licensing for the software, right? I work as a software engineer. I love computers. I love working on computers and doing cool things with computers. And damn, it sucks when like the license expires. And now, what am I going to do? Do I pay for this thing? Like, is it really a benefit? And you have to do that like, mental gymnastics. So I love owning my own tools. That's why like I've been using Vim and Linux for many, many years. So that's cool. Obviously privacy we talked on a little bit. You get to control the AI a little bit more, so you can like put in your own system prompts. You can do your, you can control like, other bells and whistles, knobs. There's infinite amount of knobs to turn with these things. But my big thing is that it's democratized intelligence, right? So as we are starting to like push more people into the cloud, right? Pushing more people into using ChatGPT or Claude or all these other things, like that becomes a little bit scary, a little bit frightening, right? What happens if those go away? What happens if the usage goes up, right? Or the price goes up, right? What if it's all of a sudden there's a model that comes out that's so good that only some people get to have access to it, right? Like Claude Mythos is like what we're seeing there, right? So I really like the idea of like democratizing this and having this as a technology that you can run and you can get to use inside your own home. I think a lot of this comes from like Richard Stallman, where it's like, proprietary software keeps the users helpless. This is a little bit of the same case. If you can't notice, I'm running this all through a terminal, by the way. This is a terminal presentation software, and I have gone through and color-coded things. These are a little bit like what the color codes mean. So, what even is an LLM? Probably like 101, right? So, I'm not going to get into like a lot of the like, it's this piece and that piece. Really all you need to know is like, we are taking a thing, a black box, and we're training it to be a next word predictor. That's really all it is, right? And then once we get to next word predictor, then we tell it to predict the other side of a conversation, right? So now it outputs word, right? And then on the other side, now we can get it to produce sentences. We say, okay, when someone comes and says this, we want to see this output, right? So we're having it kind of predict what the other side of a conversation should look like. Obviously, after we get to that part, we start rewarding it for accuracy and alignment. starting to say, not rewarding you for hallucinations and that kind of stuff, but also in helpfulness, right? Like, how helpful is it being? And then, like, I've done a lot of big deep dives into, like, how these things work, and I've done some research, and, like, that answer is always changing. The architecture of these things are always changing. What you maybe learn from a 5-hour YouTube video, like there's one from 3 blue, 1 brown, or is it 3 brown, 1 blue? I think it's 3 brown, 1 blue. Great scientific YouTube channel. He goes on this great adventure of like how everything works, but like a lot of that information is a little bit outdated now at this point, right? So the answer is always changing. Really what matters is what the tool can do for you, because they are just tools at the end of the day. This is what our application stack kind of looks like for a local LLM. So you have your hardware, which is going to be your CPU, GPU, or I shortened this to U memory, so it's unified memory for certain things like this, or for phones, right? Then you have your models, which we'll get into a little bit. So those are your model files, but they have parameters, quantizations. Then you have like an inferencing engine. So Llama CPP is the one that I put there. So you have different servers essentially that sit on top of that who are serving up your models. And then on top of that, you have your application. So your actual like chat agents, maybe you've heard of like Claude Code or any of those types of things. That is the application that is on top of it interacting with your inferencing server. So just a little crash course on hardware, right? So you have CPU, which are general purpose. You can run models on a CPU. You're probably not going to have a good time, but you can do it. It is possible. And actually, if you're using a small model, and I'll get into what these numbers mean in a little bit, small models actually can run on CPUs, and they can run perfectly fine. You don't really need full-on hardware sometimes that runs a lot of these small models. And these small models are actually surprisingly good. You probably won't want to use them for a lot of things. You'll see. You can play with it. You'll find out yourself, right? GPUs are really where things start to become very interesting because of the type of math that we are doing. It fits the type of computing that GPUs can do, which is many small calculations in parallel. If you like linear algebra is a lot of like how these things work, and we do a lot of matrix multiplication. So, and that's what GPUs excel at, is matrix multiplication. VRAM is the scarce resource on GPUs. We'll talk about why that is, but essentially that is the amount of memory that is on the GPU itself. So common numbers might be 4 gigs or 8 gigs, 12 gigs, usually some sort of power of 2. And this kind of depicts what kind of models you can run. Between the model itself and this other thing called context window, this is going to chew up all the memory and is essentially going to be used for all of that. Apple hardware. Geez, there's like 4 Apple laptops on these tables. Apple hardware is actually surprisingly interesting. Apple hardware has unified memory, which is something that we've started to do also with like cell phones and that kind of stuff, where you have GPUs and CPUs actually share the same memory. And that's pretty cool, because if you say I have 16 gigs of memory, well, so does your GPU, right? So most graphics cards, right, might be like 8 gigabytes. That's a very common size, especially with consumer GPUs. But if you're using like an Apple laptop, you can get like a 64 gig Mac Mini, right? And that's quite a lot of memory. Now, not all of it's going to be able to be used by AI, right? But some of it's going to be used for the operating system and other things that it's trying to needs to do to operate. But you can actually cram quite a lot of stuff into that memory, and that's why, like for example, there's a $10,000 512 gig like Mac Studio that was like very popular and like sold out everywhere very quickly once like home server stuff kind of started to take off. So talking about models. Models, you can just think of them as like executable spreadsheets. That's really all you need to know. That is obviously an oversimplification, but really that's what you're doing. You're going to the internet, you're downloading an executable spreadsheet full of numbers, and then you're going to execute it with an inferencing server, which we'll get to in a little bit. Generally, the larger the model, the more intelligent it's going to be. So when I start talking about the model size of 1 billion, 2 billion parameters, 4 billion, 8 billion, these are like common sizes, 30 billion, 120 billion, those are kind of signifiers of intelligence. Not necessarily because of, some models are better than others, but, generally speaking, right? There are also some little bit of different architectures in the models that you should know. So first off is like the dense models. These are the simplest to understand. So when you have a parameter in a model, right? So this is what the numbers mean. Like when we say 4B, we have 4 billion parameters. A parameter is basically one of the numbers in the spreadsheet. Okay, so there's 4 billion numbers in the spreadsheet. And what we are doing with a dense model is every time we feed it, every single one of those parameters gets executed upon. As the model is executing, every single parameter talks to every other single parameter, right? There's another architecture out there called the mixture of experts architecture. This one is very interesting. Essentially, you can still have a 30 billion or 120 billion or even more, right? A trillion parameter model out there, right? You still need to load it all into memory, but when you are executing the model, only so many other parameters are activated, right? So you often see these as like, for example, a very common one right now is this Qwen 3.6 model as a mixture of experts model. And Qwen has a mixture of experts, which is a 35 billion parameter model. And then when it's activated, it's 3 billion parameters. So they call it 35B A3B. So that's a little bit like what the numbers are, like what you're going to see, and like a little bit of behind the scenes of what those numbers mean. Yeah, and then, so now we got to talk about tokens and tokenization, which is perhaps one of the dumbest words now in computer science. But basically, what is a token? It is not really a word, it's not really a character, it is like a piece of text. It is some semantic meaning that we are assigning to it. So this is like an example. I actually had an AI write this little text box, which is like, if I have a sentence of like, I use Arch Linux, by the way, hey, I use Arch Linux, it will actually break it up into these tokens for these characters. Okay, this becomes important when we talk about like how these are fed into the model. If you are using AI, like if you're using AI in like Claude Code or anything like that, you're like, what do the tokens mean? When the context window and the this and the that. This is all it is. It's just like how the text, how it is being broken down and resembled in, or disassembled into memory. So why do we care about this? Well, primarily memory. So each token takes up memory. When you're running AI locally, we'll talk a little bit about the KV cache. That eats up memory, right? Compute as well. The more tokens you have in memory, the slower it's going to be to process. Speed as well. And then if you're using AI, if you're using any like these models outside of like off of a local network, also cost. This is typically how a lot of models are charged, which is you take a sentence, you're breaking it down, you're tokenizing it, right? And then you're getting charged per those tokens. And you typically have different cost metrics for when you're uploading to the model versus when you're generating text. But that's a little bit outside the scope of the presentation. You just know these are what the tokens mean. Context window. So it's basically how much memory can the AI know or hold about what is going on, right? So yeah, it's like everything that remembers. It typically does fall off, right? So if you're filling it up too much, the oldest things will typically get just fall off the queue, right? So it does become a little bit expensive when you're talking about local models. So the reason is that so you have the model in memory. So let's say that you have like a 4 billion, you have an 8 gig card, and you have a 4 billion parameter model. That's going to be around 2.5, 3 gigabytes. Then you have the rest of the memory in the card for your KV cache, which is the context window. So, that could be like the 128,000 tokens, right? As an example, right? But and that's a lot. This is probably enough to code most medium to small size projects, right? It's enough to hold quite a few documents in memory if you're doing like text things. But also I have also at work I've done things with LLMs where I've pushed like 800,000 tokens into context, right? I am pushing the entire project into the AI's memory. Like, hey, dude, go figure it out. I don't want to think anymore. Those types of things. Oh, sorry, what?
I said, how'd that go for you?
Actually, it went pretty well, actually.
Really?
Yeah. Anyways, yeah. So if you again, like you are working within these constraints of the model of what your hardware can do locally, right? So a smaller model, you're freeing up a little bit more of that space. You can kind of think of it as like if this is the total thing, and then this is the model, right? The smaller you make the model, the more context you can have. But you're obviously sacrificing intelligence, right? If you're doing with a bigger model because you need the intelligence, you have a smaller amount of context you can really hold. Yeah. Also, your entire conversation also feeds into the context, so that's also something to think about. There is also some new research with Google and this TurboQuant thing that made a big splash a couple weeks ago. TurboQuant is pretty cool. It actually kind of lives up to the hype, is a little bit of a marketing gimmick. I'm not going to get into like a lot of the details, but it actually is pretty cool. It actually does save a lot of space when we're talking about putting a lot of tokens into context.
And that's their new process for like minimizing the need for as much RAM, right?
Yep, correct. Talking about quantization. So, I'll actually make this a little bit smaller so it doesn't overflow as much. So this applies both to models and it applies to your context window, your KV cache. So most models, they have like the way that they are distributed, the way that a lot of these companies like Anthropic and Google run them, or if you're using Neo clouds or whatever, they are running them at the full precision, which is like a lossless amount, right? And remember, you have to all these things are they're executable spreadsheets. These are just numbers, right? But you can essentially quantize that down to make them smaller, to make up like less memory. So you can take them from like a 16-bit to an 8-bit, to a 4-bit, to a 2-bit. As you're cramming things down, you are losing a little bit of intelligence, right? You're losing precision, essentially. But you can fit like a relatively large model in a smaller amount of space. And and sometimes you're not losing that much quality. Sometimes you're not really noticing the difference between the two if it's just you chatting to it, right? There's a trade-off, of course, but it's one of those things, play with it, see how it goes. I typically run 8-bit models myself, but like for a brief period of time, I tried running. I had like a 35 billion parameter model at like 8 bits with a full context cache and all that stuff. But I actually did run at one point a 128 billion parameter model at 2 bits. And that's a huge model with a lot of intelligence to it. Of course, I'm like slamming it all the way down to ones and zeros, but it kind of worked, a little bit. It ran, it produced text, it did some things. This is essentially like, if we're talking about like loss of quality, you can kind of think of it like this. So there is a metric out there called KL divergence. The K and L stands for something that's too long to say what those words are. But basically you can think of it like this. So if this is the original like BF16, your model is a little bit smaller, right? But you're holding the same kind of quality. If you're going even lower, you're really saving a lot of space, but you start to end up with like weird things like this, right? And that's probably not good for like coding, probably not good for like text stuff, right? If you're going down to 1.5 bit, like things start to get a little weird. Probably don't go that low. Yeah, so 2-bit quants exist, but probably not really recommended. Here are some common like quantization numbers, just so that we are aware of like what they look like. There are these things called static quants. These are kind of like the old school way of doing it, which is like every parameter in the spreadsheet, is slammed down to these smaller precisions, right? These smaller numbers, right? It's simple, but it's wasteful. There's like some more in the model. And again, don't want to get too much into architecture. There are some layers or some nodes that are like more critical than others. And so that's what these dynamic quants do, is that they actually run the model, they figure out which ones are the important ones. I mean, there's some in the architecture that we know are important, but then which ones are the most commonly activated when something runs through the model. And then we are picking those and keeping those at full precision while then also taking the rest of them down. So we're saving a lot of space, but we're not really losing that much quality. It's a more smarter way of doing this type of stuff. Again, a lot of this also applies to your KV cache. So if you're trying to put a lot of tokens in the context, you can also quantize down the tokens that you're putting into the KV cache. It's just kind of like a little bit more economical. So talking about different sizes of models, this is a little bit of like the capabilities of like what you can do with these different sizes, because I've been talking about the sizes a little bit. 350 megs is like useful for small things. There's these idea of like function calling models where you can like essentially use it to on your phone, for example, and tell it to like, I don't know, change your screen brightness or do this or do that. And they can call functions essentially, right? 1 to 2 billion parameter models, you can use those, and you can actually chat with it. It works. And you can run that on like a CPU, and it's not going to be like too terribly slow either. You can do that for like summaries. You can do that maybe for a little bit of semantic analysis of sentences. There's some interesting things that people are doing with these smaller models. The 2 to 4 billion parameter models, also very surprisingly useful. You can actually hold conversations with a 2 or 4 billion parameter model. Again, it's probably not going to be too good. It's not going to be compared to like your Claude or your whatever, but it's still pretty good. 8B is where we start to see things become interesting. Okay, this is where you can probably start using it to like produce a little bit of code. Probably on like the file size level. Functions obviously, but yeah, at the file size level, generating multiple files or doing it more than maybe like 4 or 5 of them starts to become a very big struggle, but you could actually do it. 20 and 40 billion is really like the agentic barrier. That's a wide margin, but like in here, this is where you can start like plugging in my favorite tool, which is open code. You can start like actually doing some agentic workflows. This is a little bit of like, so going back to our chart, we had the hardware, the model, and then the inferencing server. These are some inferencing servers, right? So at the very bottom, you have the model. So the model is typically distributed as what's called a gguf file. Sometimes it's called safe tensor files. There's like basically those are the 2 big formats out there. Then you have these inferencing engines. These are the most popular ones. So you have Llama CPP, which is very popular. It's a little bit of like tweaking you have to do. It's a little bit more intensive, right? You have VLLM. VLLM is kind of like the turnkey enterprise version. It kind of is the fastest, but it's also a little bit pickier, and there's a little bit less options for things that you can do with it because it's designed to be deployed maybe in a little bit more of like an enterprise environment. SGLang is the new guy on the block. I've been hearing a lot of good things about it. It's very fast. That's all I really know. I do want to start messing with it, but when I get some time. But Ollama is probably one of the more like famous ones. It was really one of the first ones out there. Ollama is very turnkey. Ollama is also built on top of Llama CPP, so they actually use it as a core, and then they build on top of it. Olam is a little bit slow. It's not exactly like there's a few. It's getting a little bit long in the tooth. Let's just say that, right? It's becoming slow. It's also the other thing is I put these different API layers on here. This is typically how you're interacting with these things is through like an API, through like like HTTP calls. Like you're trying to hit a website, right? Like get index on HTML. That's typically how you're doing it. And some of these servers have like wildly different APIs and like how they're being structured. So certain tools kind of have a hard time figuring out like, is it this? Is it /API? Is it /v1? Is it this? Is it that? Right? So there's some differences there, and that one's going to be a little bit hit or miss. But yeah. The demo time. So I basically have a little script that I had. Oh, this is really small. I apologize. I had written up a long time ago. I have it loaded up with a few different models right here. And yeah, let's go play with them. So one of my favorite models actually for local stuff is this LFM2. It's from this company called Liquid AI. This is actually the smallest MOE. Hey, look, we're already using the terms. This is the smallest MOE model that I have seen. So it's 8 billion parameters of intelligence, but it's only 1 billion parameters when it's active. So this is now the server starting. This is running Llama CPP. For many reasons, that's the only server I can actually run on this laptop. By the way, I should mention, this is all running on this laptop. No internet, okay? All in this terminal. And now this is live on port 88.1. You can talk to it in the terminal if you really want to. Sometimes even I have to break out of the terminal, right? Let me refresh this. And here we are. Now we have a little text interface that you're probably familiar with. I'll make this a little bit bigger. As you're playing with models, one of the things I like to do is I like to have like, okay, I made up this term. I don't really know what a good other way to put it is, but I call them like totem questions. Kind of like, what's that movie, Inception? Right, you have everyone has the totem, right? So they know what's real and not real, right? Anyways, I know, really dumb. But my thing is that if you're testing out a lot of different models, they have a lot of different characteristics, right? Come up with a question that you know the answers to. You know what kind of structure you want in your answer, how much detail there is. Is it you want bullet points? Do you want it to be spread out with like the HR bars in them? Do you want like what are you looking for? So mine is what is a super void and how large are they? So super voids are like in space and they're really big. It's a basically absence of material in space. And so whenever I ask an AI question, I'm looking for like, does it tell me the size? Does it tell me what the Botez super void is? All that kind of stuff. So this is running on as you can see, running on my laptop. We were getting other things to know. We were getting 34 tokens per second output. Now we know what tokens are. Now we can start realizing how speeds work, right? Because you're getting so many tokens per second. You can see like, okay, this one, all right, yeah, this is what this means. Okay, yeah. We got some bullet points. We got the super voids. I didn't see anything about the Botez thing, but okay, whatever. If we swap back over, maybe what we'll do is load up a dumb model. Actually, Quen is always popular. Let's do a Quen. There's also another reason I want to load up the Quen to show something else off. Cool. So this is already up and loaded.
These are all just turnkey. You just grab them and just throw them in and then just run them and you're good.
They're all actually, even then, all the models, they all sit in a single directory on my laptop. And then I actually have, this is so silly. I actually have AI, like whenever I download a new model, I just put it in here and then I say, go update the script. And then I can just go run the script. I don't even think about the script anymore, right? Yeah. But anyways. Oh, did this already update with Quen? Nice. I think I can regenerate with Quen. There we go. So now this is Quen. You can see it's running a little bit smaller. This is a little bit bigger of a model to run, right? We went from 1 billion parameters active to now 2 billion parameters active. And we can see that I'm only getting 20 tokens per second, right? This also, I do want to point out, this is a lot slower. I think it's because I'm also streaming at the same time. I'm streaming off this laptop. So I'm doing a lot of things on here right now. It is typically faster than this. Cool. So anyway, so let's see. Yeah, okay. Well, it definitely produced text. And then I'm not going to, differentiate these in front of us. That'd be a little bit of a tedious process. But make up your own mind. You know how to run them now. You can see how it works. You can compare them yourself. Come up with your own questions. Yeah. Getting started, right? So, you have no GPU, very common. You can install Ollama. You can run Quen 3.54b, right? So that's one of the Chinese models. Very good. Oh, that was the other thing. That was why I ran Quen. So Quen also, by the way, I have image support. I can dump images into this as well. That was the whole reason I ran Quen. Anyways, but also, so Gemma is a Google model. Google releases these models every so often, and Gemma's their newest one, and they have a 4 billion parameter model that's pretty good. It competes really well with Quen. There's actually, in the small models is very interesting stuff that's going on between them and like IBM just came out with this really interesting release of like Granite 4.1 and some other things in there. If you have like a GPU, so some common GPU sizes or around 8 gigs, you can run like Quen 3.59b, right? So it's a much more smarter model. Obviously, you got to run it at like a quantized size, but that's solid for coding, solid for conversations. You can run Gemma 4b if you want a little bit more headroom for longer contexts, right? If you have more memory, right? You can start running, like this is the model I run at home, which is this Quen 35b. A lot of people, I run this 35b because it's fast. I get about 200 tokens per second output, which is very fast. But, a lot of people actually are loving this Quen 27b. They're actually finding it to be almost equivalent to like state-of-the-art models like Claude. It's not quite, but they're finding it to be pretty close and pretty usable. OpenAI also released GPT OSS. And again, in this size, you can probably start doing like agentic things like with OpenClaw or other agentic harnesses. But also, from left field, Raspberry Pi. You can run LLMs on Raspberry Pi with Pi OS. Potato OS, because it's a potato. But you can, I've actually seen some really interesting things because there's a parking lot out there. I'll tell you the parking lot story. There's someone on Reddit who just hooked up a Raspberry Pi, hooked up a webcam, pointed at a parking lot, and then put it on a script so that every so often it would take a picture of the parking lot, and then roughly estimate how full is the parking lot. Is it full? Is it not full? Whatever the case may be. And then it would just send that to like a website. And then he had a parking lot like gauge essentially on a website. He knew how full it was when he got there, right? That's pretty cool. And he's doing that on a Raspberry Pi. China's doing some really interesting things. So we were talking a little bit about Chinese models, right? So China's doing it very interesting. It's all open source. It's all open weight, weights are the numbers, the parameters, right? They're doing open training. They're like saying, this is how we train it. This is the processes that went into it. Holy shit, look at this math. There's also open research. So everything that they're doing is all open source. Now, not all of it is all open. Some models are a little bit more open than others, right? But it's also really interesting because, they're doing it open, but they're also doing it much cheaper. They're doing it like a tenth of the cost of like a lot of AI models that you are getting from OpenAI or Anthropic, right? I will say it's probably not altruistic, meaning they're probably not giving it away all in good faith. They're probably trying to just undermine tech dominance from these other companies, right? There was also a little bit of a fear of like a trigger word where like, oh, well, what if we deploy this really good model and we put it inside of an organization and then we have it running inside the organization, and then we can give it a trigger word, and then all of a sudden, like, all the guardrails fall off and it's now evil and we own it, right? And now it's, inside this organization kind of thing, right? There's like weird, interesting theories and stuff out there. But again, if all of it's open, you can kind of verify. I mean, probably we won't verify it, but in theory someone can verify it. It's a little bit like the open source question, right? But yeah, you can audit for it, right? The downloadable stuff. So we talked a little about Gemma. NVIDIA also is doing some really interesting things. NVIDIA is also doing a lot of open source with Nemotron. Nemotron actually is pretty cool. Nemotron is another really small, good model in the small sizes. In the larger sizes, a little bit of a harder sell. It doesn't quite compare to like Quen, some other stuff. Meta, Meta really fell off. Meta actually, so everything, Meta released Llama and the Llama series of models, and that is why everything is named Llama, right? Because it's LLM. So you have like open, Ollama and all this other stuff. And lately, they just really have fallen off. They haven't really published anything that's cool or interesting, all that kind of stuff. IBM Granite, I just talked about that. That's pretty cool. And, Microsoft, they got 5.4, kind of. It exists. It's there. So Nemotron is really cool and interesting. But training SOTA is the short term for state of the art. SOTA models require PhD level everything, right? Like lots of compute, lots of training, all of that stuff. But yeah, so now we're kind of going up. We're going to take a look at like the some of the applications. This is just going to be a quick thing in case you haven't done it. We've been living with very shit agents for a long time. Things like Google Assistant and Siri and Alexa. Man, they're terrible. My apartment has so many of the little Google talking lady, and they're terrible. But these are actually useful, right? So here's some like common things. Obviously, a lot of people heard of OpenClaw when that kind of splashed onto the scene in like February, I think it was. OpenCode is essentially taking over my computer. I love OpenCode. OpenCode is a coding harness, but I've extended it with like search capabilities, and it's like replaced Google search for me. It is essentially how, and now also because I run Linux and these models are very good at Linux. I can control my computer all through the terminal. I think one time, without even thinking about it, I was going to bed and I was like, put my computer to sleep. And then I walked away and then I like turned around. I was like, holy shit, it actually went to sleep. It like ran the command to put the computer to sleep. Okay. Pi is another really cool, interesting one. Is a little bit more like tied into the Unix philosophy. It's like OpenCode, but you kind of build it yourself with your own extensions and everything. It goes really fast. But it also goes off the rails really fast because there's no like safety things built into it. Bottom line, we're kind of coming to the end. Basically, I do like to own all of my own tools, and I take that very seriously. So that is why I'm very into running local models. If I'm going to form a dependency on AI as a tool, I want to own that. I don't want to pay a subscription. I don't want to have a license. I want to be able to own that experience. Granted, I will admit it is a lot of overhead of like, damn, why is it broken today? Like stuff like that. But also knowing the stack. What else is in here? Yeah. What you should take away is AI is a tool. It's not an oracle. Be aware of sycophancy and dependency, which we'll talk about in a second. Don't use AI for life decisions. But yeah, so the dark side, which is the thing I kind of wanted to talk about, as kind of get into this. Basically, AI is very. There's this term, and I had to learn this word, and now you probably are going to learn this word. It's called sycophancy. Is basically the AI through our learning process when we were saying like, hey, as we said, we went from the next word generator to the other side of conversation, right? And then we're rewarding it for like alignment and this and that. Well, part of that is that we found that the AI is starting to like tell people, oh, this is a good idea, right? You can go to it and be like, I have a business proposal for selling shampoo to poodles or something like I don't know. Thinking off the top of my head. I have this idea. Please create for me a business plan and tell me if it's a good idea. And then, it will say, yes, it is. And then like, oh, should I quit my job and leave my wife or do whatever, right? Make these huge life decisions. And be like, absolutely, because your idea is so good. Like, don't do that, right? Also, we found recently, this has just come out in the New Yorker on April 16th, like, remember in 2024, I think it was, late 2024, when Sam Altman was outed as like the CEO of OpenAI? No one knows why. Well, it's kind of starting to come out now that basically they knew that GPT-4o had really sycophantic tendencies and failed safety checks, and he still decided to push it out. And it was his board trying to remove him from those kind of decisions because it's unsafe. So that's really not good. By the way, GPT-4o did recently get shut down on the day before Valentine's Day this year, and there were a lot of people who like essentially it turned it into their AI boyfriend, girlfriend, or therapist, or whatever the case may be. And there was a very dark day on the internet where people were like yelling and screaming about how they never even got to say goodbye and all that stuff. Like it's it's very dark. Anyways,
did they roll it back too though?
Did they?
They rolled it back in less
I think
than
they rolled it
hours because of the outcry.
Yeah, I think they rolled it back once, but I think February 13th was actually the
They did it right before Valentine's
Day.
Day.
Yeah.
That's extra cruel.
Yeah.
Just knowing that what's gonna happen to people.
Potted flowers and everything.
Yeah. These are some warning signs. If you're spending a lot of time with AI, you're sharing personal details, you're seeing paranoid responses. You're being told that you have invented a new form of math. I've seen some ridiculous shit. But basically, I did want to put this in the presentation because when you are using AI at home, you are no longer limited by like your wallet, right? And there's no one really limiting you. So there is a room for abuse. And that is a very thing that is something you just got to keep in check. Especially because you're dealing with a lot like dumber models. They tend to hallucinate a little bit more, right? And also, there are models out there that people have removed the safeguards from. They're called obliterated or uncensored models. So there's uncensored, which is like it will swear and that kind of stuff. But then there's also obliterated. That's a term that's a reference to Alibaba, who makes the coin models. There's a whole history there, but basically the idea is that like that also removes the safeguard. So the uncensored is like it will swear, but it will still have safeguards. It will you can strap it to a coding agent and say hack the thing, right? Hack the Gibson, and it won't do it, right? It will say that goes against my like whatever. But if you use an obliterated model, you can say please hack this thing, and it will go do it because the safeguards have been removed. So again, concerning patterns, concerning things. If you're working at home, yeah. But basically, I think this is the end. I did want to say thanks to Jason Eastreet, my friend. Basically, I did meet Jason Eastreet at ISTS or RIT a few months ago, and I yapped to him for about 2, maybe 3 hours about AI and where I think it's going and some of the good things that I see in it, because it's not wholly bad. I think that it's a lot of like what you want to get out of the technology. There's definitely a lot of education that it can do. There's a lot of teaching it can do. There's a lot of good that can come from it, but there's also a lot of bad. And running AI at home empowers you to do the good things if you want to do them. And then I also want to say thanks to Stephen Taylor. Damn, because look at that BitHaven. Look at this. There's so many people in this space. It's so great to see like so many good people who have like interests and all those types of things. I think it's just an awesome space that we have here. So, There we go. That was the presentation.
So I got a question.
Yeah.
Do you have to worry about AI drift at all with the local models?
What do you mean by drift?
So if as we're putting things in and we're saying no, that's not it, or that's like, let's say I wanted to code something and then I tell it's wrong.
Mm-hmm.
Is it going to learn from my prompt saying it's wrong?
Yeah, it will definitely. Yeah, you can definitely say, "Oh, yeah, it's wrong," and then it might even reread its own context, like, "Oh, yeah, I can see where the format error is," or whatever.
Does it store itself and the changes and the errors that it made previously by any way? Does it like alter the actual context of its actual data sets based off of it?
Oh no,
Okay,
it doesn't.
so
do
then
that.
you don't have to worry about
No, it's a
previously
stat.
telling it messed up and then
No,
later on you're like,
it's a dumb.
oh no, it didn't, and then it comes back. and
It's a
tells you
it's a
wrong.
dumb spreadsheet, you know.
I love it.
Yeah,
Perfect.
you can pull the plug, you know, quite literally. So,
Cool.
yeah.
I thoroughly enjoyed the presentation,
Thank you.
but I came in to learn how to drive, and you taught me how to drive a spaceship.
Oh.
So, I thought it was a more of an intro course. Where would you suggest if I wanted to really get to the basics and start
Yeah.
that kind of thing?
I mean, honestly, Olama is a great starting inferencing
I
server.
don't want to
Yeah.
go alone. I would like to.
Oh well, actually, after we're done here, we have laptops and stuff like that out there that we fresh images on. If anybody wants, we're just going to grab laptops. I plan on trying to run through and set on my first one.
Yeah.
So
There
anybody
are-
wants to hang around.
And then I didn't put this in there, but you can also you can run LLMs in the browser now. They actually use like your GPU in your computer through the browser. I mean, again, it's not maybe the best experience and blah blah blah, but yeah, it is a technology that works. Yeah, you had a question.
I think I'm trying to nail down what you're kind of asking here. You touched on it a little bit when you mentioned soda. Like I'm wondering, like when something gets released, like you said, it's done learning. It's you're just playing with what they've taught it. If I have it on my own machine, am I able to train it to be like an expert in my industry or something like that? Am I able to do that?
You can fine-tune models. So there are like base models that are released, and you can get them in the full quantization, and you can feed it all the tokens you want, and you can make it an expert in your field. You can fine-tune it. I think.
to get it like okay, completely clear context window, and it still knows my industry information. That's what I'm looking for.
Probably not. I don't really have that much experience with. I don't have any experience with
just wondering
fine-tuning
how it
models.
works.
Yeah, it's you have to remember that it's more like pattern matching than anything else. So it's not going to retain any of the actual knowledge, but it's going to remember the patterns of the data,
Okay.
right? Yeah, I don't have much experience in there, and it's something that appears to have kind of waned off in the favor of like RAG for documents, but also just large context windows. Yeah.
You could probably
Build bigger data centers, and it's fine, right?
Yeah, exactly.
Yeah, that's exactly what we
you
do.
could probably build your own training set, but that gets into like, do you know how to program and use like TensorFlow
I know how to
and pull in,
Claude to program.
like pull in like the data sets specifically for that. I think there's a whole bunch of sites that have them, but it depends on what you're looking for.
Yeah.
You mentioned it a few times, and I already know. But what are the specs you're running on your laptop, just so people?
Oh,
like
it's this is an M2 MacBook Air, so it is I mean now they have the Neo, but at the time this was the lowest spec Apple laptop that they made, right? It's 16 gigs of RAM.
And he's streaming, and he was able to run terminal and
Yeah.
Bible, so.
And a web browser, because geez, web browsers in 2026, what are they doing? Why do they suck up so much memory? Yeah. Any other questions?
Awesome. All right,
Cool.
well, thanks, man.
Yeah.
Appreciate it. I'm gonna end the stream. This will be saved and uploaded later on to YouTube, so we can go back and watch it like 12 times to even keep up with your brain. Again, thank you everybody for being here at BitHaven. If you want to hang around, I plan on bashing my head against the wall trying to build one of these things, but I'm gonna drag Bubba along so he can be here to help us do it. So, awesome.
By the way, these slides are all in the terminal, and you can go to web browsers, man. But
web browsers.
yeah, well, web browsers are broken. Anyways, it's because it's all just Markdown files. This is all on GitHub. So if you have any questions, you want to see anything about the talk, it's all right there. So you can see everything is all there.
Awesome. Thanks.